At the center of nearly every galaxy spins a monster of impossible scale. These are supermassive black holes, and their existence challenges everything we think we know about the cosmos. On this journey, we will uncover 30 of their most profound secrets, from their baffling births to their potential role as gateways to other realities. By the end, you will possess a new understanding of the fundamental forces that shape our universe. We will explore why some of these giants formed impossibly fast, and what happens to matter in its final, terrifying moments before vanishing forever. What single cosmic mystery keeps you awake at night? Staring at the stars, their sudden appearance is the first great cosmic contradiction. We find supermassive black holes, some with masses billions of times that of our Sun, already fully formed when the universe was a cosmic infant. How did these giants emerge from the primordial darkness so impossibly fast? This is our first great mystery, the birth of the giants. One leading theory suggests they were born big, skipping the slow growth phase entirely. Imagine a vast, pristine cloud of primordial gas, so massive and dense that it bypasses the stage of star formation. Under its own immense weight, this cloud could have collapsed directly into a black hole, a seed already thousands of times the mass of our Sun. This direct collapse would give it a colossal head start, a king born into power. But there is a rival idea. Perhaps the seeds were smaller, the remnants of the very first generation of stars. These pioneer stars were behemoths themselves, burning furiously and dying young in spectacular supernova, leaving behind stellar mass black holes. The mystery is how these smaller seeds could have feasted and grown so rapidly to become the monsters we observe. They would have needed to consume matter at a breakneck pace, pushing against fundamental limits. The existence of these ancient leviathans forces us to question our entire timeline of cosmic evolution. It is as if we unearthed a modern skyscraper in the ruins of a prehistoric settlement. The universe, it seems, knew how to build giants far sooner than we ever thought possible. But these cosmic infants did not remain small for long. We now encounter our second great mystery, the impossible early growers. Take the quasar known as J0313-1806. This brilliant beacon of light comes from a supermassive black hole with a mass over 1.5 billion times that of our Sun. The staggering part, the light we see from it began its journey to us when the universe was a mere 670 million years old. That is less than 5% of its current age. To reach such an incomprehensible size in so little time, this black hole would have needed to devour matter at its theoretical maximum rate for its entire existence, a feat that defies our current models of physics. Think of trying to fill an Olympic swimming pool with a garden hose. Now imagine you need to fill an entire ocean in a single afternoon. The sheer scale of growth required is that extreme. How could a black hole consume so much gas and dust so efficiently, so quickly, without pushing the material away with its own intense radiation? This is the feeding frenzy paradox. The very act of eating so voraciously should have generated unimaginable pressure, blowing the surrounding food source far out of reach and effectively starving the black hole. Yet the evidence shines brightly across billions of light years, telling us that it happened. These ancient, fully formed monsters are not rare anomalies. They are signs that our universe, in its youth, possessed secrets of growth and gravity that we are only beginning to glimpse. This quietness, however, is not the only rule these giants follow. For every brilliant quasar blazing across the cosmos, there is a silent behemoth lurking in the dark. Our own galactic center is home to one such giant, Sagittarius a star. It possesses the mass of over 4 million suns, a true cosmic titan, yet it emits only a faint whisper of energy. This is our third mystery, the paradox of the dormant black hole. How can such a monstrous gravitational pit, surrounded by a swirling feast of stars and gas clouds, be so incredibly quiet? The answer lies not in a lack of food, but in the manner of its feeding. Imagine a bonfire. If you throw a massive log onto it all at once, you get a roaring, brilliant blaze. But if you only sprinkle it with sawdust, you get a weak, smoldering glow. Sagittarius, a star, is in a sawdust feeding phase. The material around it is too hot, too spread out, and too magnetically chaotic to fall in efficiently. Most of the gas and dust gets stuck in a slow, lazy spiral, taking thousands of years to inch closer, with only tiny amounts actually crossing the event horizon. This tells us that a black hole's activity is a direct reflection of its galactic environment. A quiet black hole means a stable, mature galaxy. The frantic chaos of its youth has settled down, and the monster at its heart has been largely starved into a state of deep slumber. But this dormancy is almost certainly temporary. In the future, a wandering gas cloud or a disrupted star could plunge toward the center, and our silent behemoth could awaken, transforming into a brilliant quasar once more. This cycle of feast and famine is a fundamental rhythm of cosmic life, a reminder that even the most powerful entities in the universe are subject to the ebb and flow of their surroundings. But this cosmic silence is an illusion. The universe is humming with a vibration we are only just learning to hear. Far below the range of any sound, a sea of gravitational waves ripples through the fabric of spacetime itself. This is our fourth mystery, the hunt for the gravity wave background. Scientists predict that the cosmos should be filled with a faint, constant hum, a collective echo from millions of pairs of supermassive black holes orbiting each other in the hearts of distant, colliding galaxies. Each pair, as they spiral closer over millions of years, sends out these ripples in spacetime. Alone, each signal is too faint to detect, but together they should create a steady, universe-wide drone, like the roar of a distant ocean heard from 1,000 miles away. To listen for this cosmic murmur, astronomers use the most precise natural clocks in the universe, pulsars. These are the spinning cores of dead stars, beaming out radio waves with the metronomic regularity of atomic clocks. By monitoring an array of these pulsars across our galaxy, scientists can look for tiny, correlated shifts in their rhythmic pulses. The passing of a gravitational wave subtly stretches and squeezes the space between us and these pulsars, making their signals arrive a fraction of a second early or late. It is an experiment of almost unimaginable precision, trying to detect a distortion in spacetime smaller than the nucleus of an atom. Confirming this hum would do more than just prove a theory. It would open an entirely new window on the universe. It would be the ultimate proof that supermassive black holes do not live in isolation, that they often dance in monstrous pairs, and that the merging of galaxies is a fundamental, ongoing process in the cosmos. We would, for the first time, be able to hear the background music of the universe, a low-frequency song composed by the slow, gravitational waltz of the universe's most powerful objects. Even as we listen for their cosmic hum, a deeper question emerges. How do these monstrous pairs ever get close enough to create those ripples in the first place? This brings us to our fifth great mystery, a puzzle so stubborn that scientists call it the final parsec problem. When two galaxies collide, their central supermassive black holes are drawn together by gravity, sinking toward the new combined galactic core. They spiral inward for millions of years, but then they stall. They end up orbiting each other at a distance of roughly 1 parsec, which is about 3.26 light years. To an outside observer, that might seem incredibly close, but in gravitational terms, it is a vast and empty chasm. The problem is that dynamical friction, the process that brought them this far, stops working. Dynamical friction relies on the black holes gravitationally nudging countless stars and dark matter particles out of their way. This interaction steals energy from the black holes, causing them to spiral closer. But once they reach that final parsec, they have effectively cleared out their immediate neighborhood. There are simply not enough surrounding stars left to nudge, leaving the two giants stranded in a seemingly endless orbital dance, forever just out of reach of a final, merger-producing embrace. So how do they ever cross that final gap? The universe must have a secret mechanism to finish the job. One compelling solution involves a third black hole, a smaller interloper thrown into the mix from a previous triple galaxy merger. This third body can act as a gravitational catalyst, interacting with the binary pair and flinging one of them inward through a complex orbital exchange, finally delivering it to the point of no return. Another possibility is that vast, swirling disks of gas, left over from the galactic collision, can provide the necessary drag. As the black holes plow through this dense medium, they experience a new kind of friction, sapping their orbital energy and drawing them relentlessly together until spacetime itself can no longer hold them apart, and they collide. The final parsec problem reminds us that the universe's most dramatic events are not always simple. They are delicate cosmic ballets, requiring just the right conditions and partners to reach their spectacular, universe-shaking finale. That final, violent merger is a spectacle of pure gravity. But what of the matter that feeds these giants long before such a collision? Deep within the glowing maelstrom of an active black hole, a line is crossed where the rules of orbit break down completely. This is our sixth mystery, the unseen plunge region. For decades, Einstein's theory of general relativity predicted a boundary just outside the event horizon, a point of no return for orbiting material. Until now, this has been purely theoretical, a ghost in the equations. But recent X-ray observations of a black hole over 10 million times the mass of our Sun may have finally given this ghost a shadow. The data reveals a dramatic and sudden change in the behavior of the superheated matter swirling in the accretion disk. For a vast distance, this material orbits the black hole in a frantic, luminous whirlpool, much like water circling a drain. But the new evidence suggests that at a certain critical distance, the stable orbits simply cease to exist. Spacetime itself is dragged around the black hole so violently that matter can no longer maintain its circular path. Instead, it makes its final, irreversible lunge toward the abyss. Imagine a river flowing smoothly toward a waterfall. For miles, the current is strong but predictable. Then you reach the precipice. The water stops flowing horizontally and simply drops. The plunge region is that precipice, the moment the river of space gives way to the vertical fall. Confirming its existence is a monumental step because it allows us to test Einstein's theory in its most extreme environment, where gravity is so powerful it twists the fabric of reality. By studying this final plunge, we are not just watching matter disappear, we are witnessing the absolute dominion of gravity, a force so complete that it dictates the final moments of everything that dares to venture too close. From the silent plunge into oblivion, we now turn our gaze outward to the most violent particle storms in the cosmos. The origin of ultra-energy cosmic rays stands as our seventh profound mystery. These are not mere rays of light. They are subatomic bullets, individual protons and atomic nuclei traveling through space at nearly the speed of light, each carrying the punch of a professionally thrown fastball, all compressed into a single, invisible speck. Their energy is so impossibly high that it defies any conventional explanation. For decades, their source was one of the universe's best-kept secrets. The prime suspects, the only engines in the cosmos powerful enough to forge such projectiles, are the relativistic jets screaming from active supermassive black holes. In the cores of certain galaxies, as matter spirals into the abyss, not all of it is doomed to fall in. Intense magnetic fields and the black hole's ferocious spin can funnel a fraction of the superheated gas away, channeling it into too narrow, opposing beams that blast outward at over 99% of light speed. These jets can stretch for millions of light years, far beyond their home galaxy. Within these cosmic particle accelerators, the conditions are more extreme than any laboratory on Earth. Protons and other particles get caught in a chaotic web of swirling magnetic fields, gaining a little more speed with each pass, like a ball being bounced between two converging walls. With each ricochet across the jet, the particle's velocity climbs until it is finally flung out into the void with unimaginable force. This process can accelerate a single proton to energies millions of times greater than the most powerful particle colliders we can build. Yet, the mystery deepens. How exactly do these jets achieve such perfect, efficient acceleration without the particles losing their energy or simply tearing themselves apart? Tracking these cosmic bullets back to their source is a detective story spanning the universe. When one of these ultra-high-energy particles finally strikes our atmosphere, it creates a massive shower of secondary particles, a fleeting splash of light that giant telescopes can detect. By tracing the path of these rare events backward, scientists have found that many seem to point back to galaxies with violently active black holes at their hearts. This suggests that the silent, dormant giants like our own Sagittarius A star have a far more active and dangerous past, and that their relativistic jets may be the ultimate cosmic artillery, firing the highest energy particles across the universe for billions of years. These cosmic engines of destruction may, in fact, be the ultimate architects of life. The eighth mystery is one of cosmic symbiosis, the profound and puzzling connection between a supermassive black hole and its host galaxy. Astronomers have discovered a remarkable correlation, a cosmic scaling law that seems to govern the universe. The mass of the central black hole is almost perfectly proportional to the mass of the galaxy's central bulge, the dense swarm of stars at its heart. It is as if the galaxy and its dark heart grew up together, locked in a gravitational conversation across billions of years. But which one is leading this dance? Does the black hole control the galaxy's growth, or does the galaxy dictate how much the black hole can eat? One compelling theory casts the black hole in the role of a strict cosmic regulator. When a black hole enters its active quasar phase, feasting on vast amounts of matter, it floods the galaxy with intense radiation and powerful jets. This incredible outpouring of energy can blow away the surrounding clouds of gas and dust, the very raw materials needed to form new stars. In this scenario, the black hole acts as a thermostat, switching on its fury when the galaxy gets too busy forming stars, and effectively shutting down the stellar nursery to prevent the galaxy from growing too large. The black hole's own growth is then limited by the amount of food it has left. The other possibility is that the galaxy itself is in charge. The overall gravitational pull of the entire galaxy, dominated by its dark matter halo, may control how much gas funnels down to the central regions. The black hole can only consume what the galaxy's grand structure delivers to its doorstep. It is a passive diner, waiting for its meal to arrive, its final mass simply a reflection of the bounty its home could provide. The truth likely lies in a complex feedback loop, a continuous dialogue between the monster and its home. A galaxy provides the feast, the black hole feasts, and then, with a roar of energy, tells the galaxy to stop cooking. This intricate relationship suggests that the largest structures in the universe are not random. They are shaped by a fundamental, if violent, partnership, one where the most destructive force in nature might also be a necessary guardian, ensuring the stable, long-lived galaxies where stars, planets, and life itself can eventually emerge. This cosmic feedback loop shapes entire galaxies, yet it operates on a scale of unimaginable violence. But what happens at the very edge of the abyss itself challenges our most fundamental laws of physics. We arrive at our ninth mystery, the information paradox, a puzzle so deep that it questions the nature of reality. According to the rules of quantum mechanics, information can never be truly destroyed. You can burn a book, but in theory, if you could collect every single ash particle and trace every photon of light and ripple of heat from the fire, you could reconstruct every word. The information is scrambled, but it is not gone. Now, throw that book into a black hole. Stephen Hawking famously showed that black holes are not completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of radiation, now called Hawking radiation. This radiation, however, appears to be completely random, carrying no information about what fell in. When the black hole finally evaporates and vanishes, what happens to the information about the book, the star, or the planet that formed it? According to Hawking's original calculation, it is irretrievably lost, wiped from the universe. This creates a catastrophic paradox, pitting Einstein's general relativity against quantum mechanics. One set of rules says the information is trapped inside. The other says it is erased forever. The universe cannot have two conflicting rulebooks for how reality works. So, where does the information go? Modern physics offers some mind-bending solutions. One radical idea is the holographic principle. It suggests that all the information about everything that falls into a three-dimensional black hole is not stored inside at all, but is instead encoded on its two-dimensional surface, the event horizon, like a cosmic fingerprint smeared across the boundary between our universe and the unknown. The three-dimensional reality we perceive inside could be a projection from that two-dimensional surface, a hologram of staggering complexity. Another terrifying possibility is the firewall. What if the event horizon is not a smooth, empty space as Einstein predicted, but a searing wall of energy? As one particle carrying information falls in, its entangled partner is ripped away at the horizon, creating an incandescent barrier that would vaporize anything crossing it. This would preserve information by never letting it actually enter the black hole, but it violates the principle that falling past the horizon should be an uneventful journey. The information paradox forces us to confront the fact that our understanding of space, time, and information is still profoundly incomplete. Solving it may require a theory of everything, a new set of rules that can finally reconcile the world of the very large with the world of the very small. This mathematical breakdown at the very heart of the black hole is the ultimate cosmic dead end. We have arrived at our 10th great mystery, the nature of the singularity. All the immense mass of a supermassive black hole, billions of times the weight of our Sun, is predicted by Einstein's theory of general relativity to be crushed into a single, infinitely dense point at its very center. This is the singularity, a place where the curvature of spacetime becomes infinite, and the known laws of physics simply stop working. The equations break down entirely, offering no answers, only a glaring error message in our understanding of the cosmos. Think of it as a cosmic dividing by zero. You can follow the math right up to the very edge, but at the final instant, the calculation fails. It is a sign that our most powerful theory of gravity, which has so perfectly described the orbits of planets and the bending of light, is incomplete. It cannot handle the extremes of such unimaginable compression. The existence of a singularity is not so much a physical prediction as it is a cry for help from our mathematics. It tells us that we are missing a crucial piece of the puzzle, a set of rules that can govern the realm of the incredibly small and the incredibly massive simultaneously. This is the quest for a theory of quantum gravity, a framework that would marry the large-scale world of general relativity with the bizarre, probabilistic rules of the quantum world. In this new theory, the terrifying notion of an infinitely dense point would likely be replaced by something far stranger. Perhaps there is no true singularity at all. Maybe the crushing gravity is halted by a phenomenon known as quantum pressure, where the fundamental graininess of spacetime itself prevents matter from collapsing into an infinite point. Instead of a dead end, the center of a black hole could be a vibrant, dynamic object, a knot of spacetime foam or a gateway to something entirely beyond our current comprehension. The singularity is the final frontier of our knowledge, a stark reminder that for all we have learned about these cosmic monsters, their ultimate secret remains locked away, waiting for a new physics to reveal the true nature of reality at its most extreme. Even the space around our quiet giant is a cosmic menagerie of the bizarre. Our 11th mystery takes us to the very doorstep of Sagittarius, a star, where astronomers have discovered a strange new class of object, the enigmatic G objects. They look like innocent, puffy clouds of gas, several times wider than our entire solar system. They follow long, looping orbits that bring them perilously close to the black hole's event horizon. The puzzle is how these fragile-looking clouds survive the journey. The tidal forces so close to a supermassive black hole are unimaginably powerful, capable of stretching and shredding anything that dares to approach. A mere cloud of gas should be torn to wisps long before it reaches its closest point. Yet, the G objects pass through this gravitational maelstrom and emerge, more or less, intact. They get stretched and distorted, yes, but they do not completely disintegrate. This impossible survival suggests they are not simple clouds at all. So what are they? One leading theory proposes they are bloated, disguised stars. Imagine a normal star, much like our Sun, but cloaked in a thick, extended atmosphere of gas and dust. A shroud so vast it makes the star appear as a fuzzy cloud. This dense shroud could be the result of stellar mergers, where two stars spiraled into each other and coalesced, throwing off a massive envelope of material. This central stellar core would act as an anchor, a gravitational knot that holds the entire puffy structure together as it whips around the black hole. The tidal forces pull and stretch the outer envelope, but the core keeps it from flying completely apart. Another possibility is that we are seeing the aftermath of such a merger in real time, a single star still swaddled in the cosmic debris of its violent birth. The behavior of these G objects provides a unique natural experiment. As they approach the black hole, we can watch how their material is pulled and heated, giving us an unprecedented map of the gravitational landscape in this extreme region. They are cosmic probes, sent by nature herself to test the limits of matter under the most severe conditions. Their very existence reveals that the galactic center is a dynamic and violent nursery, where stars are not just born and die, but sometimes collide and merge, creating these strange, resilient hybrids that can dance with the monster and live to tell the tale. These focused beams of destruction are born from a perfect cosmic storm. The secret of jet formation is our 12th great mystery, a puzzle of how a black hole can channel chaos into a narrow sphere of plasma moving at nearly the speed of light. The raw material is the superheated gas of the accretion disk, a swirling storm of matter doomed to fall inward. But for a select few black holes, not all of this material meets its end. Two key ingredients are required to transform this chaos into a focused jet: the black hole's own spin and the immense power of magnetic fields. First, imagine the black hole itself is a spinning sphere, dragging the very fabric of spacetime around with it like a cosmic whirlpool. This rotation creates a powerful engine. Then, consider the accretion disk, a turbulent sea of ionized gas where magnetic fields are frozen into the plasma, twisted and wound into impossibly tight coils by the disk's frantic motion. These magnetic fields act like the rails of a particle accelerator. Near the event horizon, the spinning black hole and its magnetic prison work in concert. The fields channel some of the infalling material, directing it away from the poles. As this plasma is forced along these magnetic field lines, it is accelerated to breathtaking velocities, focusing it into two thin, oppositely directed beams that punch their way clear of the accretion disk and scream out into intergalactic space. This explains why only some supermassive black holes possess these brilliant lances. A black hole must be both actively feeding, providing the fuel, and it must be spinning rapidly, providing the rotational energy to power the launch. A dormant black hole like Sagittarius' star has little fuel and may also be a slow spinner, offering no spark for this incredible cosmic fireworks display. The presence or absence of these jets is a direct readout of the black hole's diet and its fundamental state, a signature of the violent dynamo hidden within its gravitational prison. Yet for all their power, these supermassive giants seem to have skipped a crucial step in their own evolution. The cosmic family tree of black holes has a glaring gap, a missing link that represents our 13th great mystery. We have plentiful evidence for the small ones, the stellar mass black holes born from dying stars, and we are surrounded by the supermassive leviathans anchoring galaxies. But what about the middle children, the intermediate mass black holes, with masses ranging from a few hundred to a few 100,000 times that of our Sun? Their absence is a profound puzzle. If supermassive black holes grew from smaller seeds by merging and feeding, then the universe should be teeming with these intermediate specimens. They should be the crucial stepping stones, the halfway points in the growth hierarchy, yet they are incredibly elusive, like finding the fossilized bones of dinosaurs and mice, but nothing in between. Where are they all hiding? The most promising hunting grounds are not in the chaotic hearts of galaxies, but in the serene, ancient globular clusters that orbit them like distant swarms of bees. These dense collections of millions of stars are pristine relics from the early universe, and they are perfect environments for black holes to form and merge. If an intermediate mass black hole exists, Its immense gravity would cause the stars immediately around it to orbit at a much higher velocity, creating a telltale spike of motion at the cluster's core. Astronomers have searched for this signature for decades, with only a handful of tantalizing, yet still debated, candidates. One of the most compelling is in a globular cluster named Omega Centauri. Here, the stars at the very center are moving so fast that they seem to be orbiting something invisible, something with a mass of about 47,000 suns. It is the strongest hint yet of a true missing link. So why are they so hard to find? Perhaps they are ejected from their birth clusters during violent gravitational interactions, flung into the dark, empty intergalactic void where they become nearly impossible to detect. Or maybe their growth is stunted in these crowded environments, starved of the gas needed to grow larger. Finding definitive proof of an intermediate mass black hole would be a monumental discovery. It would confirm a fundamental pathway for cosmic growth, proving that the universe builds its monsters from the bottom up, one merger at a time. Until we find them, the origin story of the supermassive black holes remains incomplete, a family history with its most important chapters mysteriously blank. These gravitational giants may be anchored by something even more mysterious. Our 14th mystery plunges us into one of cosmology's most profound puzzles: the potential link between supermassive black holes and dark matter. We know dark matter exists, its gravitational pull sculpting galaxies and holding clusters together, yet it remains utterly invisible, refusing to interact with light. What if these two great cosmic unknowns are not just neighbors, but are fundamentally intertwined? One radical theory suggests that dark matter itself could be the hidden fuel for black holes. Imagine the dense halo of dark matter that is thought to surround every galaxy. At the very center of that halo, right where the supermassive black hole resides, the concentration of dark matter particles would be incredibly thick. If these particles are their own antimatter counterparts, they could annihilate upon contact, releasing a tremendous burst of pure energy. This energy could then feed the black hole, providing a steady, invisible power source that does not require regular gas or stars. This could explain how some black holes grew so massive so quickly in the early universe, feasting on this ubiquitous, dark fuel that was all around them. An even more mind-bending possibility is that dark matter is made of black holes, not the supermassive ones we see today, but vast numbers of primordial black holes, forged in the chaotic furnace of the Big Bang itself. These would be the missing intermediate mass black holes, or even smaller ones, scattered throughout every galaxy, their collective gravity making up the dark matter we infer. In this scenario, the supermassive black holes at the centers would simply be the largest specimens in a vast, invisible population, the kings of a hidden kingdom of black holes that forms the true backbone of the cosmos. The evidence for this is shaky, but the implications are staggering. It would mean that the dark matter problem and the black hole mystery are one and the same. Every time we observe the gravitational lensing of a distant galaxy, we would not be seeing the effect of some exotic particle, but the subtle distortion caused by countless invisible black holes drifting through the void. While these ideas remain at the frontier of speculation, they force us to consider that the answers to our greatest cosmic questions may not lie in separate boxes. The key to understanding the darkness that binds the galaxies might be hidden in the darkest hearts of the galaxies themselves. Could the ultimate fate of everything swallowed by a black hole be a rebirth in another reality? This leads us to our 15th mystery, the white hole hypothesis, a concept that pushes the edges of theoretical physics into the realm of science fiction. A white hole is imagined as the exact opposite of a black hole. Where a black hole is a one-way door into oblivion, a white hole would be a one-way door out of somewhere, an exit point from which matter and energy could only emerge, never enter. If a black hole is a cosmic drain, a white hole is a cosmic fountain, endlessly spewing out material. The mathematics of general relativity allows for such an object to exist, a perfectly valid solution that is simply the time-reversed version of a black hole. The profound question is whether this mathematical curiosity has any physical reality. One extraordinary idea connects them directly. Some theories suggest that the singularity at the heart of a black hole might not be a dead end, but a bridge, a tunnel through the fabric of spacetime known as an Einstein-Rosen wormhole. This wormhole could theoretically connect the black hole in our universe to a white hole in another, entirely separate universe. Everything that falls into the black hole here would be violently ejected from the white hole over there, a cosmic regurgitation of matter and energy on the other side of reality. This idea escalates into an even more stunning possibility: the notion that our own Big Bang, the fiery birth of everything we know, was itself the eruption of a white hole. In this cyclical cosmology, a supermassive black hole collapsing in a parent, four-dimensional universe could have forged a wormhole that spawned our entire three-dimensional cosmos from its white hole mouth. Our universe, in this breathtaking view, would not be the first and only, but simply one bubble in an infinite foam of universes, each born from the catastrophic collapse of another. While there is no observational evidence for white holes, and many physicists consider them unlikely, the hypothesis forces us to confront the deepest questions about our origins. It suggests that the monsters at the centers of galaxies are not just tombs, but potentially wombs, and that the ultimate secret of creation might be hidden within their impossible depths. Perhaps the greatest challenge to the information paradox comes from a radical rethinking of the black hole's very surface. For decades, the no-hair theorem has been a cornerstone of black hole physics. It states that a black hole can be described by just three simple properties: its mass, its electric charge, and its spin. That is it. No other details, no complexity, no memory of the billions of stars and planets it has consumed. A black hole, according to this theorem, is the ultimate simple object, a cosmic blank slate with no hair, as the physicists say. But what if that elegant simplicity is an illusion? A new idea known as the quantum hair conjecture suggests that black holes are not bald at all. They may possess incredibly fine, subtle structure encoded in their gravitational fields, a kind of quantum memory permanently etched just outside the event horizon. This quantum hair would not be made of matter, but of imprints in the very fabric of spacetime itself. The theory proposes that the gravitational field of a black hole retains a faint memory of the matter that created it. When a star collapses or when a book is thrown in, the information about that object is not lost inside the singularity. Instead, it subtly alters the gravitational field in the black hole's immediate vicinity. Think of it like a fingerprint left on a smooth, polished sphere. To the naked eye, the sphere looks perfectly featureless, but under a powerful microscope, you would see the unique ridges and whorls of the fingerprint. The quantum hair is that microscopic fingerprint on the event horizon, a gravitational imprint too fine for our current instruments to detect, but potentially there nonetheless. This quantum hair could resolve the information paradox by providing a permanent, external record of everything that has ever fallen in. The information is never truly trapped inside. It is smeared across the boundary, preserved in the subtle vibrations of spacetime. When the black hole eventually evaporates via Hawking radiation, this external quantum record would remain, ensuring that no information about the universe is ever truly lost. The paradox would simply vanish. While this idea is still theoretical, it represents a monumental shift in how we view these cosmic objects. It suggests that black holes are not the simple, destructive endpoints we once thought, but are instead complex entities that faithfully, if subtly, record the history of everything they consume. They are not erasing the universe's story. They are writing it in a language of gravity we are only just beginning to learn how to read. That final record of quantum hair is written with the very substance of the universe itself. But what is the ultimate fate of the matter that provides the ink? Our 17th mystery confronts the most fundamental question of all. What physically happens to matter the instant it crosses the event horizon? The classical, terrifying answer is spaghettification. Imagine an astronaut falling feet first toward a stellar mass black hole. The pull of gravity on her feet is vastly stronger than the pull on her head. This difference in force, the tidal stretch, would pull her apart, lengthening her body into a thin stream of atoms, a single cosmic strand of spaghetti. For supermassive black holes, this process is different. Because their gravity is spread over such a vast volume, the event horizon is far away from the central point of infinite crush. An astronaut crossing the threshold of a supermassive black hole might not even feel the tidal forces at first. The crossing could be, as one physicist famously noted, uneventful. But the reprieve is only temporary. The further inward she falls, the stronger the gravitational gradient becomes. Sooner or later, the stretching begins and the inevitable spaghettification occurs, shredding all matter into its fundamental components. Yet, many scientists believe this classical picture is incomplete. It relies entirely on Einstein's general relativity, ignoring the quantum nature of reality. When we bring quantum mechanics into the picture, a different possibility emerges. Matter might not fall forever toward an infinitely dense point. Instead, it could hit a wall, not a solid surface, but a region of such incredible density that the very concept of space breaks down. This is the Planck density, the absolute maximum density that physics allows before our laws completely fail. At this scale, space-time is no longer smooth and continuous. It becomes a seething, chaotic foam, a quantum fuzz where up and down, left and right, past and future lose all meaning. Here, matter would not be crushed into a singularity, but transformed into something entirely new, perhaps reborn as the fundamental strings or loops of a deeper reality. This theoretical surface would mark the true end of our universe and the beginning of a physics we can only dream of. And then there is the most speculative idea of all, that the matter does not end at all. The event horizon may not be a wall of death, but a portal. The shredded remains of a star could pass through a wormhole, a bridge in space-time, and be ejected into another universe or a different region of our own. In this view, a black hole is not a grave, but a cosmic turnstile, recycling the building blocks of reality into new realms of existence. We are left with three profoundly different destinies: total destruction at a singularity, transformation at a quantum wall, or a journey into the unknown. Each possibility points toward a different theory of ultimate reality, and we have no way yet to know which one is true. The final fate of matter is the final secret of the black hole, a mystery written in the last moments of everything that falls. This radical rethinking of reality leads us to the holographic principle, a concept so profound it redefines the very nature of existence. The seeds of this idea were planted by our struggle with the information paradox. forcing physicists to ask a startling question. What if the three-dimensional universe we perceive is nothing more than a magnificent illusion, a projection from a two-dimensional surface? This is not science fiction, but a serious theoretical framework that emerges directly from the thermodynamics of black holes. The event horizon, that one-way boundary, behaves in ways that are mathematically identical to a two-dimensional surface that can encode information. The most shocking realization is that the maximum amount of information that can be stored in any region of space is not proportional to its volume, as you might expect, but to the area of its boundary surface. Imagine a sphere. Common sense says the data you can fit inside should relate to the space it contains, its volume. But the holographic principle insists the true data limit is set by the surface area of the sphere itself. It is as if the entire rich, three-dimensional world inside that sphere, every star, every planet, every one of us, is actually a holographic movie being played from the data encoded on the spherical shell that contains it. A supermassive black hole becomes the ultimate test case for this idea. All the information about every single atom, every star, and every planet it has ever consumed is not lost inside the singularity. According to this principle, that information is perfectly preserved, painted onto the event horizon in bits of information so unimaginably tiny they are at the Planck scale. The three-dimensional maelstrom of the black hole's interior, with its crushing gravity and spiraling matter, is then just a holographic reconstruction, a cosmic mirage generated from that two-dimensional data. This means the universe itself might operate on the same principle. We may be living inside a cosmic hologram, where the true, fundamental reality is a vast, two-dimensional surface at the edge of the observable cosmos. The galaxies, nebulae, and supermassive black holes we see are all just incredibly detailed projections from that distant boundary. The solidity of your hand, the depth of space, the very three-dimensional nature of our world would all be an emergent property, a consequence of how this underlying information is processed and perceived. This resolves the information paradox with breathtaking elegance, suggesting that information never actually falls into a black hole in the way we think. It is simply transferred and stored on the surface, and our perception of a three-dimensional interior is the universe's grandest special effect. The holographic principle forces us to accept that reality may be far stranger and more interconnected than our senses will ever allow us to directly experience. This bright knot of light defies our expectations of a perfect circle. When the Event Horizon Telescope unveiled humanity's first ever image of a black hole, the shadow of M87 star, we saw a glowing ring of fire surrounding a dark central void. But the ring was not uniform. One section blazed far more brightly than the rest, a brilliant nub of intense radiation that immediately captured the attention of scientists worldwide. This was not a flaw in the image, but a crucial feature, a direct glimpse into the chaotic physics churning at the edge of the abyss. So what is this luminous nub? One compelling explanation points to the base of the black hole's relativistic jet. M87 star is famous for its colossal jet, a spear of plasma stretching thousands of light years into space. The nub we see could be the very point where this jet is launched. The moment magnetic fields funnel superheated material away from the accretion disk and accelerate it to nearly the speed of light. In this scenario, we are witnessing the birth of a cosmic particle beam, a place of unimaginable energy conversion. Another possibility is that we are seeing a temporary hotspot within the accretion disk itself. The disk is not a smooth, placid river of gas. It is a turbulent, violent storm, with magnetic instabilities and shock waves creating regions that flare up with intense brightness. This nub could be a massive flare, a clump of material glowing fiercely as it is compressed and heated on its final spiral inward. The reason the nub appears to stay in one place, instead of whipping around the black hole in a blur, is due to a mind-bending effect of relativity. The black hole's immense gravity warps spacetime so severely that the paths of light are bent into a complex dance. Light from the side of the disk moving toward us is boosted in brightness, an effect known as Doppler beaming, while light from the receding side is dimmed. This creates a persistent, lopsided appearance, a permanent signature of the black hole's ferocious spin. The presence and structure of this nub are a direct probe of the magnetic fields that govern the black hole's behavior. The brightness and polarization of the light tell us about the strength and organization of these fields, revealing how they can both fuel a jet and control the flow of matter into the darkness. This single, asymmetric feature is a Rosetta Stone for plasma physics, translating the violent, chaotic environment just outside the event horizon into a language of light we can finally begin to decode. That brilliant nub of light in the black hole's image is a testament to a hidden, fundamental power. The origins of the magnetic fields that sculpt such light stand as our 20th great mystery. These are not the simple fields of a bar magnet, but dynamic, living structures of immense power, woven directly into the superheated chaos of the accretion disk. Their generation is a self-feeding cycle of cosmic dynamos. It begins with the faintest magnetic seed, perhaps a remnant field from the interstellar gas that first fell toward the black hole. As this gas forms the swirling accretion disk, its frantic motion acts like a gigantic turbine. The ionized gas, a plasma where electrons are stripped from their atoms, carries this weak magnetic field along, stretching and twisting it with unbelievable force. Think of pulling on a tiny loop of string embedded in taffy. As you stretch and twist the taffy, that small loop becomes a vast, tangled web. This is precisely what happens in the disk, amplifying the magnetic field exponentially, transforming a whisper into a roar. But the true amplifier is the black hole itself, specifically its spin. A rotating black hole drags the very fabric of spacetime around with it, a phenomenon known as frame dragging. This motion further twists the already wound magnetic field lines, coiling them into a tightly wound spring of immense magnetic tension. The fields become so strong and organized that they begin to dictate the flow of matter itself. They act as a cosmic brake on the swirling gas, creating a magnetic friction that robs the material of its orbital energy, causing it to spiral inward toward the event horizon. Without these powerful fields, matter would simply orbit the black hole forever in a stable, quiet disk, unable to fall in and feed the beast. This magnetic friction is the true engine of accretion, the hidden hand that guides matter to its final destiny. And when the conditions are just right, when the field lines are wound tight enough by the black hole's spin, they snap. Like a rubber band stretched to its limit, the magnetic fields reconfigure, launching a fraction of the infalling material away from the poles at near light speed. This is the birth of the relativistic jet, a process entirely controlled by the strength and structure of the magnetic field. The presence of a jet is a direct announcement that a supermassive black hole is not just massive, but also a rapid spinner, and that its surrounding space is woven through with these invisible, powerful lines of force. They are the architects of the black hole's most spectacular displays, the silent conductors of the cosmic storm. This ultimate cosmic censorship might one day fail, revealing a secret so profound it could unravel physics itself. Our 21st mystery confronts the possibility of naked singularities, the most taboo objects in theoretical cosmology. A naked singularity is a gravitational monster stripped of its clothing, a black hole core without its protective event horizon. Imagine the singularity at the center of a black hole, that point of infinite density, suddenly laid bare for the universe to see. According to the cosmic censorship hypothesis proposed by the physicist Roger Penrose, nature abhors such a spectacle. It dictates that every singularity must be hidden behind an event horizon, a point of no return that protects the rest of the universe from its lawless, infinite physics. This censorship is the universe's way of maintaining order, ensuring that the unpredictable chaos of the singularity cannot affect our predictable reality. But what if this hypothesis is wrong? The mathematics of general relativity does not strictly forbid a naked singularity from forming. Under certain extreme conditions, such as the collapse of a perfectly symmetrical, non-rotating star or the violent merger of two black holes, the event horizon might fail to form, leaving the raw, naked singularity exposed. If such an object existed, it would be a window into the infinite. We could, in theory, observe the very point where gravity becomes infinite and time stops. We could see the complete breakdown of cause and effect, where the past and future become meaningless. The consequences would be staggering. A naked singularity could emit unpredictable bursts of energy or matter, violating every known law of physics. It could become a portal for time travel or a factory for creating entirely new forms of matter. The predictable clockwork of the cosmos would be replaced by a realm of pure, untamed possibility. The hunt for these objects is one of the most daring quests in modern science. Astronomers scan the skies for any strange, point-like source of radiation that defies all explanation, any flash of energy that behaves like nothing else. Finding just one would be the most revolutionary discovery since relativity, proving that the universe's deepest secrets are not always hidden in the dark, but can sometimes flare into existence, naked and terrifying for all to see. The very surface of a black hole may hold the key to its deepest secret. This brings us to our 22nd mystery, the black hole entropy enigma. In our everyday world, entropy is a measure of disorder, the number of ways you can arrange the components of a system without changing its overall appearance. A tidy room has low entropy, a messy room has high entropy. For any normal object, the amount of disorder, the number of possible internal arrangements, increases with its volume. A larger room can become far messier than a small closet, but a black hole defies this common sense rule. Its entropy is not proportional to the vast, unknowable volume inside. It is precisely proportional to the surface area of its event horizon. The amount of information it can contain is determined not by the space within, but by the area of the spherical shell that contains it. This is as bizarre as saying the number of books you can fit in a library is not determined by the size of the building, but by the area of its outside walls. This discovery, first made by Jacob Bekenstein and refined by Stephen Hawking, was a shock to physics. It suggests that the true, fundamental degrees of freedom, the ultimate bits of information that describe a black hole, reside on its two-dimensional boundary. The three-dimensional interior, with all its crushing gravity and spiraling matter, might be a secondary effect, a projection from that surface. This area law for entropy is a powerful clue that spacetime itself is not smooth and continuous, as Einstein believed, but is instead granular. It is pixelated, composed of unimaginably tiny units of area at the Planck scale. The event horizon can be thought of as a mosaic made from these fundamental pixels, each one capable of storing a single bit of information. The total entropy, the total information capacity of the black hole, is simply the number of these tiny tiles that make up its surface. This is why the area matters, because it counts the number of fundamental pixels available for encoding the history of everything that fell in. The black hole entropy enigma forces us to confront a staggering idea. The universe may operate like a colossal hologram, where a three-dimensional reality emerges from a two-dimensional surface. The solidity of the world around us, the depth of space, the very notion of volume, could all be an illusion generated by information processed on a distant boundary we cannot see. The event horizon of a black hole is not a wall of death, but the ultimate hard drive, and its storage capacity reveals the pixelated, holographic nature of reality itself. The relentless pull of a black hole seems the very opposite of the universe's accelerating expansion. Yet these two cosmic forces may be secretly entwined. Our 23rd mystery plunges into the strange and speculative possibility that supermassive black holes are not isolated from dark energy, the mysterious force pushing the cosmos apart. At first glance, the idea seems contradictory. How can the most powerful localized sources of gravity in existence have anything to do with the force that drives galaxies away from each other? One far-out theory suggests that black holes and dark energy are not just neighbors, but are fundamentally coupled. The vacuum of space is not truly empty. It seethes with virtual particles that flicker in and out of existence. Some physicists propose that the immense gravitational fields of supermassive black holes could be altering the properties of this quantum vacuum in their immediate vicinity. This local distortion might, in some way we do not yet understand, be linked to the dark energy that fills the cosmos, as if the black hole's presence is tuning the very fabric of the void. An even more radical idea posits that black holes themselves could be the source of dark energy. What if the energy contained within their immense warping of spacetime is not isolated, but leaks out into the cosmos, contributing to the overall budget of dark energy that drives the acceleration? In this view, every supermassive black hole is not just a sink for matter, but a subtle fountain of repulsive gravity, their collective influence woven into the expanding tapestry of the universe. This would mean the largest structures in the cosmos are in a delicate, large-scale balance, with the inward crush of galaxies and their central black holes subtly feeding the outward push of the cosmos itself. While these ideas are at the very frontier of cosmology, they force us to see the universe as an interconnected whole, where the darkest objects and the most diffuse energy might be two sides of the same cosmic coin, locked in a dance that dictates the ultimate fate of all we see. This boundary between our universe and the unknowable may not be a clean line at all. The true nature of the event horizon presents our 24th mystery, forcing us to ask if this famous point of no return is a sharp mathematical boundary or a blurred quantum fuzzy transition. Classical physics, following Einstein's lead, paints it as an impeccably sharp edge, a one-way membrane in spacetime that you cross without even feeling a tug. But many physicists now suspect this elegant picture is an illusion, a casualty of our incomplete understanding that ignores the quantum world. In the strange realm of quantum mechanics, nothing is ever perfectly precise. There are always fluctuations, a fundamental fuzziness at the smallest scales. So why should the event horizon be any different? Instead of a crisp mathematical surface, it might be a seething, turbulent zone, a few Planck lengths thick, where spacetime itself is a chaotic quantum foam. This fuzziness could resolve the information paradox by providing a vast, complex surface where information from infalling matter gets scrambled and stored, rather than being lost forever. The most radical vision of this fuzzy horizon comes from string theory in the form of the fuzzball proposal. This idea completely does away with the troubling singularity and the empty, smooth event horizon. In this theory, what we perceive as a black hole is actually a giant, tangled ball of fundamental strings, a fuzzball that extends all the way out to where the event horizon was supposed to be. There is no empty space inside, no sharp boundary, and most importantly, no point of infinite density. The entire black hole is a solid, though incredibly exotic, object made of these vibrating strings. The surface of this fuzzball is not smooth, but wildly complex, with strings poking and writhing in every direction, creating a massive surface area capable of storing every single bit of information about what fell in. When matter falls onto this fuzzball, it doesn't vanish behind a horizon. It simply adds its strings to the tangled mess, with its information imprinted onto the new, larger surface. This would mean that nothing ever truly crosses an event horizon, because the event horizon, as we classically imagined it, does not exist. The information never gets trapped. It is always right there, encoded in the complex structure of the fuzzball's surface, waiting to be slowly released as Hawking radiation. This is a universe without singularities and without information loss, a cosmos where black holes are not bottomless pits, but the ultimate information storage devices. While the fuzzball remains a theoretical construct, it points toward a future where our most terrifying cosmic monsters are transformed into the most complex and ordered objects in existence. The universe's grandest collisions often leave two monarchs vying for a single throne. When galaxies merge, their central supermassive black holes are drawn together by gravity, but the final act of this cosmic drama remains shrouded in mystery. How do these two behemoths, each the ruler of its own galactic domain, end up locked in a tight orbital dance? This is the puzzle of supermassive black hole binaries, and directly spotting them has proven incredibly difficult. The main challenge is sheer distance. Even the closest galactic cores appear as a single, unresolved point of light to our telescopes. We cannot simply point a telescope and see two distinct black holes circling one another. Their light is blended into one. So astronomers must become cosmic detectives, searching for subtle, indirect clues. One telltale sign would be a periodic flicker in the brightness of a quasar, the brilliant beacon of an active black hole. If the quasar's light dims and brightens in a regular, repeating pattern, it could mean that a second, unseen black hole is orbiting the first, its gravity periodically tugging on the accretion disk and altering the amount of light we receive. Another clue lies in the strange, zigzagging paths of jets spewing from some active galaxies. A wobbling jet could be the signature of a binary pair, with the jet's direction changing as the black hole that powers it is swung around by an invisible companion. The future of this search, however, lies not in light, but in listening for the faintest ripples in spacetime. As a supermassive binary spirals ever closer, it emits a steady, low-frequency hum of gravitational waves. Our current ground-based detectors cannot hear this cosmic drone, but upcoming space-based observatories, like the Laser Interferometer Space Antenna, or LISA, are being designed specifically to tune into it. LISA will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, using lasers to measure tiny distortions in space caused by these passing waves. Detecting the gravitational wave signal from a supermassive binary would be the ultimate confirmation, allowing us to measure their masses, their orbital distance, and even track their slow, in spiral over years. Finding these hidden couples is crucial because they are the final, fleeting stage before a collision that will shake the fabric of the cosmos, a monumental event that forges an even larger giant and sprays the universe with gravitational waves, telling the story of how galaxies and their dark hearts truly come together. The violence of a quasar can forge a galactic habitable zone. This 26th mystery asks if the monster at the galactic center could be an unlikely architect for life. We typically think of a black hole's fury as purely destructive, a force that sterilizes entire regions of space with its blistering radiation and relativistic jets. And for any world orbiting too close, that is certainly a death sentence. But on a much grander galactic scale, this destructive power might also be a creative one. The intense energy and shock waves from an active black hole can sweep through a galaxy, pushing vast clouds of gas and dust outward. This does not just clear the central regions, it can actually compress these gaseous materials in the galaxy's outer halo, triggering intense waves of new star formation far from the dangerous core. Imagine a forest fire. It destroys the old growth at the center, but the resulting ash enriches the soil at the periphery, leading to a burst of new life in a ring further out. In this galactic analogy, the supermassive black hole is the fire, and the new stellar nurseries it sparks in the distant spiral arms are the fresh, fertile ground. This creates a galactic Goldilocks zone for life, a ring where conditions are just right. It is far enough from the central radiation to avoid sterilization, yet it is seeded with heavy elements cooked in previous generations of stars and now scattered by the black hole's outbursts. Within this ring, a star like our Sun could form with a stable planetary system, on a world rich with the ingredients for biology. Our own solar system may exist in such a benign ring, a quiet suburb shaped by ancient outbursts from a now dormant giant. This suggests a profound cosmic balance, where the same ferocious energy that prevents life at the center may be essential for cultivating it in the galactic outskirts, making the most destructive objects in the universe potential, if unlikely, guardians of life itself. Deep within the violent glow of an accretion disk, astronomers have detected a strange cosmic heartbeat. This is the mystery of quasi-periodic eruptions, a series of powerful, repeating X-ray flares that burst from the vicinity of supermassive black holes with the regularity of a ticking clock. For hours, the region will blaze with intense energy. Then the flare will fade, only to return again hours or days later in a predictable, rhythmic pattern. It is as if something is swinging close to the abyss, getting torn apart, and then swinging back to be torn apart once more. The leading suspect in this cosmic crime is a stellar victim trapped in a punishing orbit. Imagine a star, or more likely a dense, Earth-sized stellar corpse known as a white dwarf, on a highly elliptical path around the supermassive black hole. On each close approach, the immense tidal forces strip away layers of its outer material, like a planet passing too close to its sun. This stolen gas does not fall directly into the black hole, but rains down on the inner edge of the accretion disk. The sudden dump of fresh fuel causes the disk to overheat violently, igniting a brilliant X-ray flare that we see as one eruption. The star then swings away on the long, elliptical part of its orbit, only to return on its next close pass and repeat the entire destructive process, creating the observed rhythmic pattern. There is, however, a more complex and terrifying possibility. Could these eruptions be caused by a second, smaller black hole orbiting the primary one, a stellar mass predator dancing with the supermassive giant? In this scenario, the smaller black hole's gravity would periodically plow through and disrupt the primary's accretion disk, stirring up the gas and causing it to heat up in a brilliant, predictable flash. The quasi-periodic eruptions would then be the signature of this monstrous binary, a gravitational timer counting down the moments until the two finally merge. Deciphering the true source of these cosmic heartbeats is crucial, because each possibility reveals a different facet of the violent environment near a black hole. If it is a star, we are watching the slow, methodical death of a solar system, a dissection played out over countless orbits. If it is a smaller black hole, we are glimpsing the final, pre-merger stages of a binary system, a preview of a much larger gravitational wave event to come. These regular flares are more than just flashes of light. They are a precise clock, ticking in the heart of darkness, allowing us to map the gravitational landscape and witness the intricate, repeating ballet of destruction that unfolds at the very edge of oblivion. The rhythmic ticking of a cosmic heartbeat gives way to a far more profound disturbance in the fabric of reality. Our 28th mystery asks if the supermassive black hole is not just a trap for matter, but a potential engine for time. The theoretical possibility hinges on a specific type of black hole, one that is not static but spinning at a significant fraction of light speed. This is a Kerr black hole, named after the mathematician who found the solution to Einstein's equations. Its rotation is so violent that it does not merely drag space around with it, it drags time. The region just outside the event horizon, known as the ergosphere, becomes a whirlpool of twisted spacetime where nothing can remain stationary. Within this chaotic zone, the equations of general relativity suggest something even more bizarre could exist, a closed time-like curve. This is a path through spacetime that loops back on itself, allowing a traveler to return to their own past without ever exceeding the speed of light. It would be a cosmic racetrack where the finish line is also the starting gate. Imagine following a path that seems to lead you forward, only to find you have arrived at a moment before you even began your journey. The black hole's immense gravity warps the timeline into a circle. This is not science fiction, but a stark, mathematical prediction from our most trusted theory of gravity. Yet, if such paths exist, they unravel the logical foundation of the universe. The classic grandfather paradox emerges with devastating clarity. What if you traveled back in time and prevented your own grandfather from meeting your grandmother? Your birth would then become an impossibility, meaning you could never have traveled back to interfere in the first place. The universe cannot tolerate such logical inconsistencies. So, does nature forbid this? Many physicists believe a principle of cosmic censorship, or perhaps the yet unknown laws of quantum gravity, would always intervene. The very act of trying to enter a closed time-like curve might create a feedback of energy that destroys the path, or forms a singularity that blocks it. The black hole might possess the raw gravitational power to bend time, but the universe itself may have safeguards to prevent the timeline from tearing. This leaves us at a breathtaking precipice. The same monsters that crush matter into oblivion might also hold the key to journeys through time, a power so profound that the cosmos seems to have built walls around it to protect the orderly flow of cause and effect. Even the slow, steady tick of Hawking radiation will eventually run down the clock. The ultimate destiny of a supermassive black hole is not to rule forever, but to fade away over timescales so vast they dwarf the current age of the universe. For a typical supermassive giant, this process of evaporation would take over a googol years, a number written as a 1 followed by 100 zeros. This is a span of time so incomprehensibly long that every star will have burned out, every galaxy will have dispersed, and the cosmos will be a cold, dark, and nearly empty void. In this distant, frozen era, the black hole's evaporation would finally become noticeable. It would begin to lose mass, slowly at first, then accelerating in its final moments. The smaller it gets, the faster it shrinks, its event horizon retreating inward as its gravitational grip weakens. What would this final evaporation look like? It would not be a quiet flicker. In its last second of existence, the black hole, now no more massive than a small mountain, would release all of its remaining energy in a tremendous flash of radiation and particles, a final, brilliant shout in the eternal silence. This explosion would be the last significant event in a region of space that had been dark for eons, a fleeting firework in an infinite night. The profound meaning of this evaporation is that nothing in the universe, not even these gravitational titans, is truly permanent. It suggests a cosmic cycle where even the most concentrated structures of matter and energy are ultimately recycled back into the background hum of the cosmos. The universe that emerges after the last black hole vanishes would be a profoundly different place, a thin, cold sea of fundamental particles and radiation, holding only the faintest memory of the galaxies and giants that once were. That final, silent evaporation might not be the end of the story. Our 30th and final mystery dares to ask the ultimate question: are these supermassive black holes not tombs at all, but gateways? Could the crushing gravity of the singularity be a cosmic turnstile, an entrance to another universe entirely? This is the realm of Einstein-Rosen bridges, theoretical tunnels through the fabric of spacetime more commonly known as wormholes. The equations of general relativity allow for such a structure, a shortcut connecting two distant points in our universe, or perhaps a bridge linking two separate universes. In this breathtaking vision, the singularity at the heart of a black hole would not be a dead end, but the throat of the wormhole itself. Everything that falls in would not be crushed into nothingness, but would emerge from the other end, spewed out of a white hole in another reality. The journey, however, would be far from a gentle cruise. The theoretical wormhole inside a real, spinning black hole would be violently unstable. The moment even a single particle tried to pass through, the tunnel would likely collapse into a singularity faster than light could travel through it, slamming the door shut forever. To keep this cosmic gateway open, you would need a form of exotic matter with negative energy density, a substance that counteracts gravity and props the tunnel walls apart against their own immense weight. We have no idea if such a material can exist in the quantities required, or if it is merely a mathematical ghost. Even if a traversable wormhole could exist, navigating it presents another universe of problems. The tidal forces at the entrance would still be powerful enough to spaghettify any known material, and the radiation flooding the tunnel would be lethal. Furthermore, the one-way nature of a black hole's event horizon means you could never turn back. You would be committed to a one-way journey into the complete unknown. This idea pushes the boundaries of theoretical physics to their absolute limit, blurring the line between science and science fiction. It suggests that our universe might be just one bubble in an infinite cosmic foam, with supermassive black holes acting as the delicate threads stitching these realities together. While we have no observational evidence for this, and the practical challenges are currently insurmountable, the possibility remains a profound and haunting speculation. It transforms the most terrifying objects in the cosmos into symbols of ultimate potential, suggesting that within every ending could lie a beginning we cannot yet comprehend. From the very first moment we realized these giants existed, they have challenged our understanding of reality. We have traveled through 30 profound mysteries, from their impossible births in the cosmic dawn to their silent, gravitational dominion over entire galaxies. We have questioned how they grew so vast so quickly, how they can be both dormant and violently active, and how they might be secretly linked to the dark matter that binds the cosmos. We have stood at the edge of the event horizon, grappling with the information paradox and the terrifying nature of the singularity, where physics itself breaks down. We have listened for the hum of their mergers in the gravity wave background and witnessed the strange, resilient objects that dance around them. We have explored the holographic principle, which suggests our three-dimensional reality may be a projection, and considered the radical possibility that these monsters are not tombs, but gateways to other universes. Each unanswered question, from the final parsec problem to the nature of Hawking radiation, is not a dead end, but a frontier. They are signposts pointing toward a deeper truth, a more complete set of laws that govern everything from the smallest quantum flicker to the largest structures in existence. These mysteries push the boundaries of physics because they force us to invent new mathematics, to conceive of new dimensions, and to question the very fabric of space and time. So now we turn this final question over to you. Of these 30 cosmic riddles, which one captivates your imagination the most? Is it the potential for time travel around a spinning black hole, the eerie survival of the G objects, or the mind-bending idea that we might be living in a holographic universe? Share your thoughts, and never stop looking up. Never stop wondering about the profound and beautiful mysteries that lie waiting